Okay, so let's start today's class. We will last week we stopped at the lasso estimate, and we will have a quick review about the lasso estimate. So we have a mention. We're just starting in this chapter. We're starting with the ridge estimate, where we consider additional terms, so the L2 penalty in our objective function. And for the lasso, we're considering by remove the L2 norm to the L1 norm. So L2 norm mentioned that stand for the stand for we use a beta square. So we consider the every element wisely. So we consider every coordinate of the beta and taking the square as additional penalty. And for lasso, we consider the absolute value. And we mentioned that the lasso have a good property that it can handle. So a high dimensional data, and it's actually built on such kind of the assumption. So we assume that the ground truth of the beta. So here so the model is like, we consider that we still focus on this type of model and with a beta star. So here, once we adopted the lasso, so its underlying logic is that we assume the beta star, the ground truth of that term, have a sparse solution. So which means that most of the element in the beta star is zero. So that means in reality, or in this type of data, when we adopted this model, we always have this kind of thinking. Maybe not every um our feature, so z feature of z will contribute to y. That will stand for the corresponding beta star is zero. And the lasso is just built on that. So we have mentioned. So actually it's starting from that. If we assume that the non-zero element, so it's just some fixed number. And this is our original objective function. Where we assume that the ground truth. And so because of this kind of consideration, so when we solve our problem, we should take in this kind of consideration. We also call as a constraint. So if you know something about optimization, so just because we know it's our result should have this type of property. So therefore, when we solve this problem, we just put this one as our constraint. So to guarantee our solution will also have this property. And we mentioned that this one is pretty hard to solve, and a very, very smart idea is to transform this type of the optimization problem to this lasso type problem. And eventually we can guarantee our solution also have this sparsity. So which I means then most of the element of the beta or beta hat. So if we use a beta hat to stand for that, most of element will equal to zero. And how much of the element will close equal to zero just depends on the value of the lambda. When lambda is small, when lambda is zero, so there is no difference compared with our lasso and the least square estimate. But when lambda is close to infinity, it's definitely that every beta should become zero, just because we can treat the objective function as a two-part, and lambda just play a role as a how to balance which part will take more importance. So like beta is close to infinity just means the second part is more important, and we're trying to argument this part, and the only solution is that all the beta is zero. Okay, so this is some things we will trying to demonstrate. Okay, so I'm trying to demonstrate. So how about for the intermediate part? The intermediate part will also guarantee most of the beta hat is zero. Okay, and to solve this type of problem, we will introduce a thing called as a counter line. So actually, this is just for illustration, just to give us some thinking. So why we solution of the lasso definitely have a sparse result. So the sparse I emphasize is just sparsity or sparse solution, just stand for when we solve the lasso, this problem, most of element is zero. That stands for, so it's a p-dimensional vector. Okay, p-dimension, and I mean sparsity just stand for most of this p-dimension stand for the p different element. So a vector that is given as a p1 hat, the beta 1 hat to beta p hat. The sparsity stand for most of them are zero. Okay, most of them are zero. Some of them maybe non-zero, but most of them are zero. This stand for the sparsity. Sparse solution. Okay, so this terminology stands for. Well, for the counter lines, here we first will give some illustration about so why the solution should be sparse. The counter line stand for here when we consider a three-dimensional function, and actually it's very multi-dimensional function. It's very hard to draw this type of function. It's pretty hard to draw. Just like 3 dimensions look like this way, and 4 dimension we cannot imagine what's the how to look at this type of function. But we can use a projection way to look at this type of function, so which called as a counter line. So which means that we can project the whole kind of the function here, so to a 2-dimensional plane, and the red part is stand for our original function, while the following projection stand for our counter line. And this counter line just tell us one type of information. Here we use a different color to stand for the counter line, and we can find the counter line is consisted by several circles. So several circle, and so like the green, like the blue, like the purples, and the light blue. And here is just stand for. So in this type, when we just draw a circle like this way, so that stand for at the corresponding coordinate. So for example, in the 2 dimensions, there is a coordinate to this type of the data. So with the x-axis 1 and with the y-axis 0. And this just stand for every element. So taking this type of the coordinate. So taking this type of a coordinate will satisfy that when we take him back to our red part function, they have the same value. So for example, if there are two types of the x1 and x2, if there are 2 points, and we use the x1, y1 to stand for this coordinate, and use x2, y2 to stand for this coordinate. This counter line just simplify, just stand for that if we denote this function as a f, and that corresponding to they have the equal value. So therefore, this counter line just stand for every circle. Every circle they have the equal value. So therefore, it's not hard to imagine that this type of circle will not have the overlapping. Will not have the overlapping. Once have an overlapping, just stand for. So it cannot have the overlapping because every value here is stand for the same value. Okay, same value. And then this type of things can help us to have such kind of the understanding about the high dimension function when we just put on the 2-dimensional plane. Okay, so this counter line is not just is quite used for in the geography. So where that the people just use this type of thing to draw a mountain. So it's just like a mountain, and use this one to stand for this line. Just stand for every coordinate here have the same height of the mountain. Well, and then our next thing is trying to use this type of counter line to understand so what is the solution of this lasso. So the most important thing or most difficult thing come from lasso is that so this one does not have an explicit solution just because it doesn't like when we use the L2 norm. So we can take the gradient to the beta, but at this moment, though it's the absolute value, and absolute value, once we take in the gradient, it may have the value like the positive 1, negative 1, and also when at the point that x equal to 0, we don't have any. We don't have it's not differentiable just at that point. So which means that when we're trying to use the gradient to solve this problem, it's not suitable. Okay, just because of this kind of consideration. Okay, we are not able to find the explicit solution of the lasso, and so therefore it's difficult for us to understand what is the solution of this one. And but we can just rethink about this problem. We can find this one just to be a combination of the two category. So one is this one. Okay, the y minus z beta. These are square arrow, and another is this one. So this one, and of course, just like we can try to plot these two type of the function, and then our solution must be some balance between these two type of the term, balance two type of term. So just the sum, we no, at this moment, we no longer minimize this. We no longer minimize this. We should try to balance this type of things. So therefore, we will draw this two function and trying to find, so where is the solution to this? And this is an old, very, very famous graph. So that's actually trying to draw the two counter line. So this draw a counter line. This is our mean square. This is our square arrow. So which is a y minus z beta square. And this one stands for a counter line of the beta, absolute value of the beta. This is the beta one. And for the next part is stand for the beta L2 no. Okay, L2 no. And this type of things we will draw these two counter line and also mention how we find the solution according to the two counter line of the function. Well, to go through that before, so given a counter line, we will define a very important concept, so which we call it as a tangent line. So tangent line stands for that will give tangent line, first of all, it's a straight line. And this straight line, our counter line, just like a curve, it's a curve. And the tangent line will, for example, if we say it's a straight line is a tangent line of our counter line. So for example, we say it as a tangent at this kind of point. And then that stands for, we will have the straight line. So cross with our counter line with this type of circle only at this type of point. So that things we call it as a tangent line. And also like this type of the line, so it's also the tangent line of the intermediate circle. So where it's only have one exact one intersection with our circle that stands for a tangent line. And the tangent line, so in geometry, it always stands for, so if you actually in geometry, tangent line just stands for the gradient of the function. So at this moment, so the tangent line, so actually when we're taking the function, when we're taking the gradient and the corresponding, we can obtain the corresponding vector, the gradient value at this vector. So that is this angle, and the tangent line in geometry just stands for the gradient. Okay, and this is for the usual function. And in addition, so we will also need to consider, so what is the counter line of our lasso part, so which is our this type of the penalty, So what is the counter line and what is the corresponding tangent line? So for this usual part, so this tangent line is usually just looks, this counter line is always looks like this type of a form. And how about for the another part? So so this is a counter line for the absolute value part. And let's just look at, so what is this stand for? Okay, counter line of the fxy, so who will equal to the absolute value of x adding the absolute value of the y. Actually, it's just like this kind of the rectangle. Look at it this way. So it's actually a square one. And it's just we can just think about this point as a 1, this point is a 2, this point is 3. So the one that most close to the original point. So this type of the thing is corresponding to this counter line corresponding to that x plus y's absolute value is equal to 1. Okay, it's just like, look at it this way once we use the absolute value. So it's a little difference with our square arrow. Square arrow is that if we consider that is x squared plus y squared, and then it will looks like a circle. So the circle looks like this type of form. Okay, so it's a different. So actually, so this is just a two different type of function, and therefore the counter line of our penalty part, which is standard for the L1 norm, will looks like this type of form. And we also wondering, so what is the type of the tangent line here? What is the type of tangent line here? The tangent line, I mean, is actually, so just for the curve part, that stands for it's only across this type of just across with one type of the element. But for this type of things, the tangent line is a little be special. So for example, if where I can consider a tangent line here. So actually its tangent line is just looks like is exactly itself. So it's a tangent line is exactly itself. Okay. So it's a little bit different. It's a little bit difference. And so and so it cannot be a cross. The cross just stands for so one value is inside, one value is outside. So that stands for the cross. So you should guarantee it should this line is at one side of this counter line. But there are some special points like the coordinate point. The coordinate point, like this point, I just highlight here. So you can imagine what is the tangent line here. The tangent line here is actually we have the infinite. So like this is our tangent line. Okay. And we can also consider this is also another type of tangent line. So therefore, what I want to emphasize is that for this type of function, the tangent line at some special point will have the infinite one. And this point is the point in our coordinate, So we will have the several points. You can see every coordinate part will have the infinite tangent line. So this is something we need to keep in mind. Okay, this is something we need to keep in mind. And now our theory actually told us one effect is that so once we consider the two function, so where is a fxy, we consider minimize such kind of function fxy, adding the lambda gxy, the two type of function fxy and gxy. And where is our solution? So the minimum solution must be the point. At this point, two kind of either the function f or either the function g, they should have the same tangent line. So that is our solution. So that is we write down here. So a minimizer must be point where two counter lines share a same tangent line. So that must be our solution. Well, and let's just look at how we understand this one. Okay, so how we understand this one. Now I just have a function f and have a function g. So where our f is this black one and our g is this blue one. And now I draw the counter line of the f. So there are three circles. And I also draw the counter line of the g. There are another three circles. And I also point out what is the value I given here. So this is for f and this is for g. And now we want to use the question we point out here. We want to just what is this type of things stand for? So it stands for a minimizer must be the point where the two counter lines share the same tangent line. Okay, here we highlight several types of the point. So from A to I, okay, A to I, and we need to consider. So where is the point? So I just have highlight with the 9 point, and we're wondering. So where is the point that these two counter line share the same tangent line? Maybe we just look at from the top part, so which is our G. We can find, so where is the tangent line? So from the G part. So from our, also from this type of the function. So you can find the tangent line is here. So this is a one tangent line. And how about another tangent line? So tangent line at this point for another counter line is here. So it's definitely they are different. They are different. Okay. So this is G is not something we pursue. And similarly, we can consider this H point. So whose the two tangent line also does not have the same. It's not same. But for this there are three special like the ABC, and they are share the same tangent line. This is this one, this one, this one. Okay, and for the D, E, and F, it's also the same reason that they do not share the tangent line, and they cannot be our solution. So how this type of thing, what is this type of thing want to say? So why is the point? Why is the point? Minimizer must be the point that they share the same tangent line. Is this just because, as I mentioned, the tangent line just play a role like the gradient. Okay, like the gradient So once they f and the g, they have this at this point, they have the same tangent line, just means they have the same gradient. And then you can image that once you're adding these two functions, actually, they will corresponding to that. The gradient will somehow will cancel with each other, and eventually to the point where gradient will equal to 0. So that is the idea is just somehow like this. Okay. And just because of this reason, we are always trying to seek. So where is a point so that shares the same tangent line? But in reality, we know that there are so many there are just like here, the counter line is actually infinite. Just for the different value, you will have a counter line. And which type of the point we can find, okay? Which type of point, which is our final minimizer, so A or B or C. So actually, this just depends on which type of value of the lambda we choose. Like this function, f and g, we can consider the special case where lambda equal to 0. And according to this type of the counter line, we just suppose the minimum value of the f is here. So I cross this point. So this is the minimum value of the f. And similarly, we can find, so from the outside to inside, the value of g is also decreasing. So which means the minimizer of the g is also somehow here. Well, I also cross this term. So it's not hard to image that. So like the lambda equal to 0, our solution must be here, where we only have the f. When lambda is infinity, our solution must be here, where we only focus on the g. So therefore, when lambda is intermediate value, we are actually trying to find a path. So which this path will go through from lambda equal to 0 to lambda goes to infinity, and across every point where they share the same tangent line. So eventually, so our solution must be looks like we can just have such kind of a solution path. So this path follows the way that our lambda is increasing. So at this point, lambda equal to 0. At this point, lambda equal to infinity. And depends on the value of lambda, we are actually trying to go through this path. So once we increasing a lambda value a little bit, and then we will become more and more close to this point. And ABC is actually some kind of path we will go through, some kind of the point that we will go through. Here, I just point out the so it's just so the lambda is play a role. So at this moment, we look at lambda as a play a role of our how to balance the function f and the function g. So once again, so when lambda is 0, so this is solution. When lambda is infinity, this is solution. But actually, we need to handle the arbitrary positive lambda, and actually it goes through this whole path, and it will cross the ABC point. So this is how the lasso path, how the solution of the lasso will looks like. Okay, it must be in this type of the path. And now we will try to, okay, so this is just for the general function f and g. And now we will focus on our special function and trying to answer why the lasso will have the sparse result. Now this is our counterline of the lasso. We just use this one, so it's just like the lot of kind of block, and it's corresponding to the case that the absolute value of beta 1 and beta 0 adding together, beta 1 and beta 2 adding together. And the key insight thing that where we at this special point in the coordinate, they will have the infinite tangent line. Okay. And now I also adding the function of the f. So f is a counter line. So we have shown before, it looks like this type of approach. So therefore, we just draw a part of that kind of the counter line. So we use the blue one to stand for the counter line of the f, so which is our y minus z beta square. And we use this black one to stand for our counter line of the absolute value. And now we're just wondering, so where is the solution path? So where is the solution path? And of course, we just mentioned that. So the smallest value here, we just stand for smallest value, where we can get us to make f beta at the minimum, at the smallest value. So this is our least square estimate, okay, least square estimate. And the point that can make the g, the L1 norm of the beta as small as possible is here. And now we want based on our counter line. So we want wondering, so where is the intermediate point? So there are several intermediate points. Let's look at them one by one, okay? So here is one intermediate point. There is one. So it's absolute. So this one, the tangent line at this point, they share the same tangent line with our F and with our G. So we also just mark this one. And we also need to, we can also just mark one by one. So like this point, this point, this point, and other type of the point. Okay, other type of point. And once we connect all the things together, we will have such kind of the solution path. Okay, we will have such kind of solution path. So where the lambda equal to 0 at this point and lambda equal to infinity is at this point. Okay, so this is one possible solution path once we solve the lasso estimate. So for different lambda, so the solution is just in this type of path. And there is a pretty important things, pretty important things, is that it's still, so what is our solution looks like? So what is our solution looks like? How the solution could be a sparse one? Well, so actually just we already have some hint. We already have some hint, okay? So it's just like, it's more easily that they will have the same, the point that have the same tangent line is in the coordinate, Here, so there are 3 points. There are 3 points. They are in coordinate. So we first think about, so what is stand for the point in the coordinate? That is corresponding to one at value will equal to 0. Just like here, if we use this line to stand for the beta 1, they stand for the beta 2. And then every point plot here will corresponding to their beta 1 equal to 0, just because they are in a coordinate. Coordinate just stand for some part of the value is 0, okay? And but here you may just think, because I draw the blue one like this way, but actually indeed it's just because once we just draw just because the coordinate point will have the infinite, of course, for this black one, they will have the infinite tangent line. So therefore, it's more easier to make this one of the infinite tangent line, so matching as a tangent line of the blue one. So just because of this reason, it's more easily to do, because at the coordinate point, it will have the infinite one. So it doesn't like later on when we look at the ridge estimate. So ridge estimate is also like the smooth curve, not like this type of the non-smooth block. And it's so for every point, it only has the one tangent line. But for this type of the lasso, so there are several special points that have the infinite tangent line. And in that kind of way, it's more easily our solution path will in the coordinate, okay? So this is the reason why we see the solution is sparse, because it's more easily to go to the coordinate side, and the sum of element will become 0. So this is the key insight of this lasso estimate. Okay, so this could probably answer, so why is the famous, this type of the famous machine learning book will give you this type of thing, just because this point is share the same tangent line. And also for the lasso estimate at this type of a point, it has the infinite tangent line. So therefore, it's very easily that this type of the counter line will matching at this type of this point. Okay, matching this point. And so this is the main reason. And our ridge part actually look like this way. So ridge is a circle, and for any point in the circle, it only has the one tangent line. So we don't have any guarantee that it will more easily to matching at the point at the coordinate size. So we don't have any kind of the guarantee for that. But for lasso, we have such kind of guarantee just because it is more likely to do that. But it's not just likely, we can also demonstrate in mathematics, but this is a way for us to illustrate, for us to understand it. So this is a key difference. So hopefully you can, so at this moment, you can understand the key difference between the lasso and the ridge. So this is a very, very important concept in the machine learning book. So even though it's just like it's just a one norm and two norm. So it's a absolute value also with the square is a square of the beta. So, but it's definitely two different things. Okay. Okay, so we will look at for the ridge part. For the ridge part. Okay, so now this is our f, and this is our ridge part. This is our ridge estimate. It's a circle. Okay, ridge is a circle with it's actually the standard circle, and the ridge is a ellipse. Okay, it's an ellipse. It's just also some curves. And now I just want you to take 1 minute to think about, so what is the solution path in the ridge? Okay, so let's look at together. So first of all, we can also point out where is our starting point, where is our end point. Our starting point is from the lambda equal to 0. So it's this point and also this point. We first mark these two. And then we will consider where is the point that have the same tangent line. Actually, it's very, very clear where we have the same tangent line. It's this point, the following the point. Okay, we have mark them, and then we will connect the things together. Okay, so this is our solution path looks like. And from this type of thing, lambda is from 0 to lambda to infinity with the increasing of lambda. So you can see, even though our final destination of this path is still the original point, but it does not look like lasso where it directly jump. So at this moment, some kind of the coordinate starting become 0. So and eventually it jump to the 0 looks like this way. But for the ridge, you can say it does not just the path does not have the overlapping with the coordinate. So this is the reason. This is also difference. So the ridge cannot guarantee any sparse solution. So maybe some point is sparse, but not every point is sparse. So once you increase in lambda, it will eventually slow down and close. Eventually will the magnitude will decrease and become more and more close to 0. But will some type of the thing will not direct thresholding to 0. Okay, so this is a difference. And this is a some type of solution path. Okay, and now we can, and this is just some understanding from the illustration, and we will also provide more numerical evidence. Here, I show how the value of the lambda will change in the ridge estimate. So in total, I consider there are 5 features. In total, 5 features. So different values stand for the different value of the feature. And I also put their initial value. So when lambda is 0, they can from here. So some is at the 100, some at around the 30. And one thing we can observe is that, so in the x coordinate, I increasing the lambda. So this is just follows our solution path, where at this point is our least square. So at the end point is 0. So we can look at how the value will change. Here I just point out the absolute. I guess I point out absolute value here. So we can see that each line, even though it eventually will become to 0, but it's just smoothly slow down and goes to 0. So this is how the ridge, and this is also somehow matching. So it's just slow down with some certain rate, and become more and more close to 0 when the lambda increasing. Well, for the lasso, you can find it's quite different. So at some certain point, it exactly becomes 0, like this type of point. So when lambda equal to around 100, every point will become 0. So it's not close to 0, it's exactly 0, but directly jump to the 0. So, and you can also say that some of the values starting like this purple one will first jump to 0. Oh, it's not purple, it's a green one. First jump to 0, and some others also jump to 0. So that is also standard for the case. Once we increasing our lambda, we will have some sparse solution. Some kind of the coordinate will become 0. And then when we're increasing more and more, coefficient will become 0. And this is also matching why with intermediate value we can have the sparse solution while ridge will not have. And this is key things about lasso. So some things that I think you should keep in mind is that how the lasso have the sparse solution. So this is the reason why we adopt lasso. Lasso can guarantee we have the sparse solution. Guarantee we have the sparse solution. But you can find, so in other kind of the concept, if your solution is not sparse, it's very, very few cases that you adopt lasso. You know, actually, what is the reason? The reason actually just because once you use the lasso, your solution is actually the bias. Some value like some other value, some of value will be moved to 0, but some of other non-zero value is actually contain some bias. It's not such kind of accurate one. So we can see, so this is the reason. So just because the sparse result, you can use the lasso. In other case, actually, we do not just recommend for the lasso, and you will find ridge is more usual case. Okay, just for the case that most of beta, you have some knowledge in prior that most of beta is 0. Okay. And now our next question is how the people solving the lasso, and under some special case, can we give us the explicit form for lasso and other estimate? So here we consider a very, very special case where our X transpose X is an identity matrix. So actually I should write down as you can also treat it as our Z times Z, Z transpose times Z is identity matrix. And in this type of thing, the lasso is equivalent to solving this type of problem. So it's a difference between the beta and the absolute value, beta and the least square estimate, and adding such kind of a corresponding penalty. And the solution of this question could be using the thinking of this hard thresholding problem. So whose the solution will become like this way. So in this special example, the lasso estimate is equal to this type of thing. So we can look at, so what is this stand for? So actually, we can obtain the lasso estimate from the least square estimate. So when least square estimate is larger than lambda over 2, and the lasso stands for this one will be minus lambda over 2. So least square minus lambda over 2. Once this value, the absolute value is smaller than lambda over 2, then it will become 0. And once this is a very small, smaller than negative lambda over 2, then we will add in the lambda over 2. So one thing you can look at the difference from the lasso and the least square is that it makes the large value close to 0, and it makes the large negative value also close to 0. And the intermediate value will directly become the 0. So this is what we call it as a hard stress holding, directly putting the value. So directly change the least square estimate. So for the small value to 0 and the large value close to 0. So and this is the so actually you can understand this is the common user ReLU function here. ReLU function here. So it's a shrinkage the big coefficient by a constant lambda over 2 towards 0 and truncate some small coefficient to 0 exactly. Just like the example I gave here to you, you can find why every element is 0 here. Just because the least square is 100. And at this point, I just matching around 200 value. So every point is thresholding to 0, okay? Thresholding to 0. And we can back on this solution and to compare the least square ridge and the lasso. So once the Z transpose Z equal to identity matrix, this square is here. The ridge is equal to the ridge as least square over 1 plus lambda. And the lasso is something we already see. It's a thresholding term. So one thing we can observe is that actually ridge is divided by some 1 plus lambda value. And the lasso is directly shrinkage. So this looks like just consider a proportional shrinkage. So it's divided by some positive value and some value larger than 1. So this is also the reason. So even though it looks like when lambda is become close to infinity, so this term it will become 0. But for any positive value of the lambda, this one is non-zero. So this one will not have the sparse result, but this one will not. Just because you can understanding. So when lambda is large, then the magnitude of the beta, least square estimate, then this term will become zero directly. So we have a ratio here. So once this magnitude is smaller than lambda over 2, it will become 0 directly. So this also explain why I mentioned this one is why I mentioned this type of function is smoothly decay, just because taking a rate like the 1 over 1 plus lambda. So how much, even though lambda is large enough, but it still will not make it as a 0. But here, taking this type of the hard stress holding, everything will become 0 once its value is smaller than the lambda over 2. Okay, so this is how we compare. So in this special example, but for more general case, we can also demonstrate they have the same properties. Like we use the lasso have this threshold, like the higher stress holding, and the ridge is done not also close to 0. But we may take some more effort to do. So we will not show here, but just to give you understanding about the difference here. Okay, so we will end this chapter. So we will end this chapter by taking one exercise. Okay, you can first take a look and think about how we solve the first sentence. First sentence. Okay, so let's look at together, and then so we will focus on the first part, and the next part will become your assignment. Okay, so we focus on the first part. Well, so actually they both of things share the same, either the first part or second part just use the same technique, and actually it's just some. So we first record the definition of the beta hat. The beta hat of range is corresponding to the argument of this type of the objective function. And we want to demonstrate that the square error of the beta hat will increasing as lambda close to 0. In other words, we want to demonstrate. So if we have the 2 lambda, and the lambda 1 is larger than lambda 2, so therefore stand for the lambda 2 more close to 0. And then we want to show we want to show this one. We want to show the square arrow. Actually, it's not necessary to have the square. We want to show this type of thing. And you know this one is the same as the we're taking the square because this term is a positive. So we want to demonstrate. For lambda 1 is larger, we'll have the small value. Well, it's just considering how we demonstrate this type of thing. So actually, there is no, we just taking the lambda 1, lambda 2 inside the corresponding objective function. So for example, we know the beta hat lambda 1 is the smallest, is the one that taking the smallest value of this function. So therefore, this function, okay, must be smaller than, we replace this beta hat with any value, with any other beta, with any other beta. So we will adopt the beta hat lambda 2. Okay, I use a different color to emphasize. Okay, this is the function of the beta. And then the beta hat lambda 1 is the point that achieves the minimum. So therefore, this is the minimum of this function. And if we're using other beta, it will definitely have a large value compared with this left part. Well, similarly, if we change as a lambda 2, and at this moment, this type of thing change as a lambda 2. So the beta lambda 2, beta hat lambda 2 is also the one achieve the minimum value of this type of objective function. And it will also keep that. We're just taking, we just because we just need to compare these two. So then we just adding, we just change the, so this is the one making this type of function have the minimum. And this is the one making this one have the minimum. Well, you probably know what I'm trying to do. Next thing is that, so just because this term is larger than this term is larger than this term. So if we treated this term as a, this is a B, this is the C, and this is a D. So we can obtain one thing is that, so A minus C is much larger than B minus D. So this one is more small. This one is more larger. So A minus C is larger than B minus D. And then we can look at, so what is the value of A minus C? We can say A and C share the same first part. So A minus C is this term minus this term. So it's a lambda 1 minus lambda 2. Right, A minus C. And B minus D is also that they share the same first part. It's like so. And just because lambda 1 is larger than lambda 2. So this is a positive value, positive value. So we can delete, we can divide this term, and then we obtain our solution here. Okay, so this here is a common trick that we take in the beta hat as it's the optimal solution. So therefore, when we want to compare these two, so we just change the order of in the corresponding objective function and obtain the corresponding inequality. And this can also help you to show that for lasso estimate, once we change this two norm as a one norm, it also shares the same property. Okay, so we have already finished the part of the region and lasso. We will take the 10 minutes break and then we will go to the kernel method. Okay, so we will go to our new chapter, so which is named as a kernel method. So kernel method is a very famous method. So before the born of the deep neural network. So that is another very it's a very well-known method just because it can have a good performance on the for the nonlinear as a nonlinear model. Okay. So usually, so when we have our data xi and yi, and our previous model always focused on the linear model, so which we assume directly that our y and x have a linear relation, and that is our linear model. But in reality, sometimes our model may looks like this type of data. So it's just look at directly, we may not have a linear trend of the data. And that is the reason why sometimes we will adopt it, the non-linear part. But the linear function and the nonlinear function have a huge difference. Actually the nonlinear just stand for the function that is not linear stand for nonlinear, and it's just back to our original question like so. Our original question say our y, we want to find the f to making our y equal to fx. Our linear model just give us one solution that we can making it as a x transpose beta, and that is a special assumption on the f. But well, if for a nonlinear function, it could be have a plenty of the choice, and actually we do not have any kind of good idea about at the initial. We don't have any good idea about how the f should looks like. So therefore, that borns the kernel method. Kernel method is a way that we can build the nonlinear function. And so we can before we look at our today's content, so we will first have some high level idea about so what is the kernel method stand for. And then when we go through the detail, you may find there are such kind of a gap between the thing I mentioned to you with the method we will introduce. And at the last point, we will build the connection between the things I mentioned and the kernel method. So previously, when we focus on the y equal to fx, so y equal to fx, and our first approach is adopted as a linear function. So what that is stand for fx is equal to x transpose beta. So sometimes we can add in the epsilon here to stand for some noise. And the kernel method stand for. So we are wondering, so how could we making the function to nonlinear? And we also wanted to use some advantage of the x transpose of beta. So this is a very straightforward that we believe that we can first take some transformation on the x, and then after we do the transformation, that corresponding the result will depend on is also linear with the feature that we take in the transformation. So that is a nonlinear or kernel method. So kernel method will say that we will consider a function phi x. So it's some function, it's a nonlinear function, and then our fx could treat it as a phi x transpose with a beta. So phi x transpose with a beta. So that then eventually, so as long as we know the phi, and then we can handle as a linear model to solve this problem. And this is a very standard approach for kernel method. And actually, so why the kernel method could be popular? Because actually how we define a phi, we can according to some certain family of the phi. And then we can demonstrate that we can use this approach to approximate the nonlinear function. So this kernel method, if I directly use this type of the form to show you, so you can find it's very like the you can also like looks like the deep neural network is also look at as this way. Look at it this way. So you can think about the reason why. If you have ever implement like regression neural network, so multi-layer precision, you will know that they will told you after you put your final hidden layer to your outcome, do not take any activation function. Just use a linear line. Just use a linear line. So this is because the first you taking several kind of the hidden layer and until you to the last layer. So this is the value obtained at the last layer, and then you take the linear transformation. So linear transformation of your last layer to obtain your regression result. So therefore, so either the kernel method or the deep learning method, you can regard it once we adopt it like this function, nonlinear function phi, or like you adopted the neural network. Actually, we are trying to do the feature engineering that we wanted to pick up the feature. So and to make some transformation and eventually that we can make our feature after transformation is a linear relation with our y. So this is some key concept. And the deep network is a good, just is a key kind of reason is that, so compare with the kernel method, we believe it could be adaptively choosing the feature, adaptively do this feature engineering. While kernel method, you should do it by yourself. You should choose a phi x, okay, phi x. And but some kind of good earlier results say, so as long as you can choose a good phi, or all like the neural network, so why they are popular just because this phi or the neural network, you can guarantee it can approximate any smooth function, So which means that even the original function space is hugely large. So, but once you adopted this type of form or the neural network form, you can guarantee they are close enough. So therefore, we no longer worry about. So actually, we are still trying to do the search over the whole function space, but actually, we just do some. We focus on some special phi, also focus on small neural network with some certain architecture, and but the good thing is that they will close. You can close to any smooth function. So this is the reason why you can handle the nonlinearity. Okay, so this is a key concept of the kernel. But once I started introduce the kernel method, you cannot find any relation between this type of thing and the method I will introduce. Just because one reason, this reason is very special. You can look at, so you can image that our original x may be the p dimension. But how size could be our phi x could be. Phi x may not a p dimension. It could be a huge dimension vector. So it can be, so you can consider like when you have the linear model, you can also have the quadratic form and you will have more kind of features. So generally this phi x, the dimension of this term is huge large. And sometimes we do not use this type of things just because it's hard to describe what is the dimension of the phi. So later on we will say in some of the function, the corresponding phi, the dimension is the r infinity. So it's an infinity dimension. Well, that is that. So therefore, usually when they adopted the kernel method, so even though the idea looks like here, but when you do any calculation, you will try to avoid this phi. We are trying to avoid to considering what is the exact phi here, but actually we just adopted some phi to do that. Well, so this is some things we should keep in mind. So even though it looks at a little weird when we starting introducing the kernel method. Okay, so this type of the kernel method is a little bit complicated compared with any things we have starting, like the lasso, like the ridge. So this one is a little bit complicated, and I think this is the in the previous semester, student will say this is the most complicated chapter. Okay, so if you have any questions, so you should ask. And we will try to slow down once we take in several examples. So we will try to handle example one by one. So just because complicated of this session. Okay, so at the beginning, I will just make such kind of the following statement. So this statement like, suppose that we have the data xi and yi. In the ridge regression, what we are trying to do, we are trying to find some coefficient cix, ci, some coefficient ci, to making this term is close to our y part, close to our y part. So which means that our prediction is actually built on some coefficient ci, and then it's such kind of the linear combination with the inner product of xi and some new coming data x. So the beta hat x in what I mentioned before is actually stand for the beta hat times the x. So that is the inner product between our beta hat and x. So beta hat is our ridge with x. So the first statement I point out here, I just point out here is that the f hat x is actually could be retreated as a, we are trying to find some ci just like the way we find some ridge. We are trying to making the f hat of x as the inner product between xi and x. So that is to say, when we're trying to make a new kind of prediction, we are trying to build on the similarity between the xi and x. So this inner product somehow like the similarity. So if they are close, they will have the large value. If they are not close, they will have the small value. So therefore, we are trying to build on the similarity between the xi and x. So that is we have the n data. A new data just come from this n data, and how our new data not come from this n data. Just when we want to make a prediction over this x, we are just need to using the information here, and how the yi, how our prediction will looks like. It looks like we compare the xi, the similarity between xi and x. So of course, when xi equal to x, you close to x, so we should our f hat x should close the value with the yi. So this is a key idea. Okay, so this is a key idea of the ridge. But you can try to do that. You will find our earlier statement is slightly different with this type of form, just because when I write down our beta hat ridge, the solution is z transpose z, adding the lambda n I inverse z transpose of y. So if you're using the beta hat ridge times the x, you will find there is a gap. You can find it's not hard, it's not easier to identify. So what is the CI it is? So even though I told you your solution, but actually we can do. So once you use this type of the inner product, you will have this type of the form. Okay, this type of the form. So this is just based on this form, we will have the generalization from the linear to nonlinear. So this type of things just told us we use the inner product to describe the similarity between the x and the xi and x. So therefore, a very straightforward idea is that can we make any generalization on the xi transpose x to any other type of the similarity? And this type of thing we will call it as a kernel method. So the kernel method is trying to replace this inner product with some nonlinear way. Let me highlight. So we will try to change the inner product between xi and x to more general approach. This is the kernel method. Inner product could be regarded as a function. Let me write down. Okay, inner product is a function from x times x. This is the space of our coefficient to the r. So which stand for xi and xj. The pair of the xi and xj will be mapping to the inner product between them. And our kernel method will try to generalize this type of the function. And this is we call it as a function k. So we will generalize this inner product to a function k. So, and this function should satisfy the following property. So we will, naively speaking, so we will need that our k is as a positive kernel. And the usual way we will say it's a positive semi-definite kernel, positive semi-definite kernel. And it should satisfy two requirements. The first requirement is to say for any two element in X, so U and V, this K should be symmetric. So KUV must equal to KVU. This is the first statement, first requirement. Second requirement to say for any sequence x1 to xn, so a sequence coefficient, not coefficient, sequence feature, and any constant sequence C1 to Cn. We need to guarantee that the summation I from 1 to n, summation j from 1 to n, Ci Cj times Kxi Xj must be positive. So this is once it satisfies these two requirements. Actually, I need two different color to do. Let me. So there is a two requirement. The first is here. The second is here. We have two requirements. And then if we can rewrite our K as a new function, new kind of matrix, capital K. So which is a Kx, so whose element, whose IG's element is a, let me write down, is a K Xi Xj. And then this type of thing we could write as a quadratic form. That is a C transpose K times C is a positive. So this is the reason, just because the last of things, we probably know why it's called as a positive semi-definite kernel, just because when we introduce a quadratic function, if you still remember, for the in the linear algebra part, when we introduce a quadratic function, quadratic form, so we will say a matrix satisfies this type of thing. We will call it as a positive semi-definite matrix. So here it's just explicit to say K is a positive semi-definite. Well, so let's just rethinking. So first requirement is easy to check, the symmetric, and the second requirement is more hard to check. So it stands for you should consider any n data with a corresponding n sequence. This result must be positive. So it's a Ci Cj times any Kxi Xj. So then the K is this type of the function. So whose ij's element is a Kxi Xj. So here one thing we can observe is that K is a symmetric, just because the first property, just because of first property. Okay, so this is our definition. So therefore, actually, when we just handle this type of problem, the kernel method is actually we need to try to find this function capital K, and then we will try to replace our inner product to the capital K, and then we will get our solution a nonlinear approach. So here we will, and the most of effort we put in this chapter is trying to look at how many kind of kernel we could have. So here we will starting from some example. Well, we consider several kind of example. So first of all, Kxy equal to the inner product between x and y. So this is a positive kernel. And second one is that the exponential of the negative x minus y, the square of the norm of x minus y is also a kernel. So we can write it explicit form. So I from 1 to p xi minus yi square. And our last one is the 1 plus inner product x and y and takes the d power. Actually, this called as a Gaussian kernel. It just looks like our Gaussian function, Gaussian random variable. So it's a density. This is very like our Gaussian random variable. Okay, and this is a polynomial kernel. It's a polynomial function. And then, so here we have, here's just some example, but we probably just curious about. So why is this kernel put here is satisfy this type of a property? this type of property. Okay. Well, maybe we just skip this one first. We're taking these things as a granted, taking this thing as granted. We first look at, so how we solve the problem once we have this kernel, how we replace this inner product with the kernel to find a good nonlinear approximation F here. Okay, so now just suppose we already have a kernel, but we should have a question about how to which kind of kernel we can have, and we will do this once after we first understand which kind of method we will adopt it with this kernel to make the data analysis. Well, the first thing that I mentioned before, that we will directly generalize the inner product to the kernel method by replacing the inner product to the kernel function. So previously, this term is a x, y, and x. Okay, x, y, and x. So we can say this kind of approach is actually is a standard. So if you do more like the research, so like the methodologies in the machine learning, you can look at this type of thing. From the inner product to the kernel is a very, very standard approach. So we're trying to make the thing more generalized. We generalize our method to more general case, and it can solve more general problem. Okay. Well, this is our f hat. And how we just, and now our question is that, so given the kernel K, capital K, how we find the corresponding CI? So of course, the CI must be the minimizer between this type of thing with our y, so with our y. And then we can use this function to build we can build this following objective function. So here we are trying to find a C. We are trying to find, let's just back again. Okay, back again. So we are trying to find a C. And once we have a C, we can make a prediction. So this type of function we plotted here is from the Gaussian kernel approach, a Gaussian kernel approach. So it's just can directly give us this non-smooth curve, this smooth curve, but it's not a straight line. Okay, some things that we may sometimes wondering, so is that, so actually, if you can try and do some simulation, just like in the case that xi is only one dimension, you can find the kernel can give you a very good solution. So in contrast with the neural network, they are just the same performance. So why the kernel nowadays is become more hard to do, just because it cannot handle the multi-dimension case. The computational cost is very high. Okay, but for the low dimension, it can still be a good one. Okay, small low dimension is still a good one. Okay, some things just I want to say what is why this one is not popular today. Well, let's just back. Okay, so now I already have the K function, and I'm wondering, so what is the CI? So of course, the most naive approach is that, so we can treat this one as a function fx. Okay, fx. So the only unknown thing is the CI. Of course, how we find the CI? We can build the difference between fxj with the yj. And then we can build the difference. So taking the xj inside just stand for this type of thing will change as the xj. And we're wondering, we want to making this term is close to the, well, it's not yi, it's yj. We want make this term is close to this term, and then we can take in the square arrow. And then after we take in the square arrow, and then it looks like the least square estimate. But here's something we need to solve in the C here. Okay, but unfortunately, if you directly do this one, you will not have a good result. Okay, just because that you should also, just because that we need to take that corresponding matrix is not invertible. If you like the least square, if you still remember that we guarantee this guy is invertible. So therefore, we need to adopt the ridge penalty. Okay, our solution will eventually, this is our objective function. So maybe we are trying to understand. So what is that? So this type of thing, you already pretty, we have already seen what is that. So if I just use the fx to denote as a j from 1 to n, cj, kxj, nx. Okay, so this first term is fxi. So we compare different I. So this whole term, we can treat it as a 1 over n summation I from 1 to n fxi minus yi squared. So it's a very standard least square estimate. And the additional term we're taking here is our lambda times the C transpose times the KC. So that could treat it as a bridge penalty. Here, you may wondering, so why we have the K here? So it's just like when we handle the ridge, that part is also looks like the inner product. So it's generalized to the kernel part. But a more kind of reason probably that you can also adopt it to the C, directly use the C transpose C. But actually, well, it's just to make your result a little bit different. But it's probably we can also adopt it here. But in your case, we will directly taking a K here. The most of reason that you will find more easier with this K when we're taking the calculation. Okay. Well, I should not clear. Okay. So this is our kernel method. Okay. And then we can just rewrite the whole part. Just record our K function, whose ijth element is a k xi xj. And then this part of thing is actually, you can treat it as a one row of the function. So from kx1 xi to the kxn xi. So it's a one row, and it's with a summation of cj. So it's a inner product. It's not inner product. It's a vector c times one column of the k, and then minus the corresponding yi. Minus the corresponding yi. And then eventually, if every, and then we can treat this one as a k times the c minus y. So this is a one element. So it's here. So the jth element, kc minus y, the jth element is a summation j from 1 to n, cj k xj xi. Therefore, the eventual outcome, the objective part is look at as a, so every element, so it's here we consider every element in kc minus y, and eventually that corresponding to the square of norm of kc minus y. And the remaining part, we just change this 1 over n, take a here, so it's become this type of thing. So eventually we will have the kc minus y and adding the and lambda c transpose kc here. Okay, so this is our objective function. So we just make it a little bit change. So with a matrix form, Well, at this moment, so just have a quick record. Okay, have a quick record. So the objective function is come from the least square estimate, but it's actually if you do this one directly, you will find there are some issue. So we will taking this one to guarantee that we can have the inverse. So as this additional term, and eventually it will result in, we use a matrix form, it will result into this type of function. And after we do that, what is our next step? Well, we can just show this one. Okay, we can show this one. how we find the solution, it looks like this way. So it's not straightforward. Maybe we can just say why we can just first look at, so what is the solution of this argmin objective function? Now we already have the function matrix K. So whose element is whose ij's element? So I and j both from 1 to n. So this matrix have the form. So whose the row and the column is same as the data. So it's n times n matrix. And our objective function or our optimal point is the argmin kc minus y, adding the lambda n c transpose k times c. Well, now it's back to our earlier result. How we find the solution of the C star? How we find solution of C star? So we have already done some range. So maybe you can take 1 minute to think about how you find the solution of the C star here. So actually, I may go to a little quick when we just write down this form as a matrix form, but actually you can take some time to redo this one by yourself directly. Okay, so actually it's just you can regard this as a f this minus y. So just this is the one element of the kc minus y. So that is easy to write down as a matrix form. But how we get solution as a k plus lambda I inverse times y? Okay, so we will just follow our earlier approach. So actually, I should write down this one a little bit. I cannot write as an argmin. I should write as a belong. So this is may just because the solution may not be one solution. So it may be like a set of the result. And this is one possible solution of something we will adopt it here. Well, after we take in the gradient, so we will obtain that is like what is the result for this term? It's a k transpose kc minus y 2. So this is the first gradient. Second gradient is the 2 lambda n. Let me check what is the dimension here. Okay, so this is the n times n. This is c is our n times 1 part. So this is n times n. So this is 1 times n. So eventually we should have the n times 1's result. Okay, k times c. And then we want this guy equal to 0. We want this guy equal to 0. So we just reorganize the whole term. So that is a k transpose kc, adding the lambda n kc equal to the k transpose y. K transpose y. So we just make some reorganize the term. And then, so what is our solution will looks like? So what is our solution will looks like? So we combine the C together. C is something our objective part. So this type of the thing. And our question is, so how the C will have this type of result? So eventually, if the whole term here is invertible, we know that we can, if this whole thing is invertible, we can take in the inverse. We can take in the inverse. But here you can find a little gap between. So we can reorganize this one a little bit. I just using the K transpose, adding the lambda n identity K times C equal to K transpose times Y. Well, you can find there are some little gap here. Okay, some little gap here. And this little gap we will make use some statement we will use later to demonstrate with some little. You can try to take in this C star inside. You can find it may not looks like directly. The whole term will looks like the K transpose Y. You may think about, so what is the next step to solve? Next step to solve. Okay. So here, so we will just left here. So you may just think about, so what is the what is how to find the gap here? Find the gap here. So some things we can just make it more simple just because the K is symmetric. So we can change later as a K plus lambda I because the symmetric of the kernel. Okay, so it's just pretty close, but well, it's pretty close. But still have some little bit difference, some little bit difference. Okay, so you can try to solve. Well, so one thing is I mentioned that once you're taking this inside, it's just a one possible solution, one possible solution. It highly depends on whether your K is a whether our K. It highly depends on whether our K has a zero eigenvalue or not, have zero eigenvalue or not. Just like here, it's to say it's a positive semi-definite. So this type of thing may imply this term has a zero eigenvalue, zero eigenvalue. In the case that we have zero eigenvalue, so we cannot find the unique solution. Okay, so this is a little bit different compared with our usual ridge regression part. So this we just put a problem here. Okay, problem here. You can think about the reason. So probably we will, if we today we have enough time, we will answer this one. So at the end part. So actually apply the same technique. Well, now the remaining question is that, so actually kernel method will be very easily to adopt, very easily to adopt. So that is once you define your kernel, once you figure out, you prefix your kernel, and then the everything is that you compute the capital K, compute the lambda I inverse and times Y. That is your C star. And when a new data comes, you directly use this form to make a prediction, and then you follow the everything. You just finish everything in the kernel method. So everything is pretty easier. Okay, so but the usual case is that, but a common question is that, so which type of a kernel we should adopt? So which type of kernel we should adopt? Well, let's just look at, so we will try to answer this question. So after we've seen different kernel, okay, so that will also give us a hint about, so what is the function, what is the phi function we are actually use? So what is the relation between the kernel function, so with our phi x transpose beta. So what is the difference between them? So actually, we will use several. So once we can handle every example I put in this chapter, I will around have the 10 examples. We will have more and more understanding about what is the phi. So given in the kernel method. Okay, so we will first together to solve a very, very simple one. trying to demonstrate the inner product kernel is a positive definite. So this is the kernel, the requirement of the kernel. And that is to say, for any sequence of xi and, and any sequence of ci, that this whole term should become non-negative. Okay, we will try to do this first type easier thing together and see one or two more examples, and then we will try to take some time. I will give you some time to handle the remaining kernel part. Okay, so let's just focus on the first simple version, where our kxy is equal to the inner product. The first of things we should to do is to check the symmetric. I think you have no issue from here. So they are symmetric. The second one is that we should show for any xi, I from 1 to n, and any sequence ci from 1 to n. So here we can consider xi is a p-dimensional and ci is a one dimension. And the kernel method require us to demonstrate the summation I from 1 to n, summation j from 1 to n, ci, cj, inner product xi and xj. It should become non-negative. Okay, how we demonstrate this type of things. So of course, the usual case that we demonstrate a non-negative is trying to put everything as a square of something. We want to put it as a square. And this can demonstrate it's non-negative. And this is also the things what we are trying to do at this size. Okay, so we will together to show the first example. Well, here we will adopt a very important concept in the kernel, in the inner product. We call it as the linearity of the inner product. Ax adding the b inner product with the y will equal to, for any constant of a and b, this will equal to a x y adding the, I should not write b as a constant. Okay, b is adding another vector. I just use this version, it's enough. This version is enough. Axy, so it's same as a times xy. So a times the inner product of xy. And also same as x is ay. So when a is a constant. So therefore, this imply we can put the cj inside with xj. Just because here our a is looks like a cj is just looks like the a here. And similarly, ci is also the same as a. If we look at this one together. Well, so we have already handled the ci and the cj inside. Next of thing is that we will take the summation over j from 1 to n. J from 1 to n. So this we will make use another type of things. X, y1, adding y2, adding y3. Collinearity say this term is a inner product between x and y1, x and y2, and x and y3. So therefore, the C1, X1 play a role as a Y1, C2, X2 play a role as a Y2, C3, X3 plays a role as a Y3. We have the n element. We can adding every element together, And by adopted this type of thing, we obtain the summation I from 1 to n Cixi summation j from 1 to n Cjxj. Cjxj. Well, you probably know what is a key here. Next step, this type of thing is same as a y1 plus y2 plus y3x because of the symmetric. So which means that our first term could handle. We can also add in the summation over the first term by keeping this whole part as a keeping this one as a whole part, and we adding the summation inside. So maybe I write down the detail. So it's like the y1x, I adding the y2x, adding the y3x. And eventually, once we adding them together, is a summation I from 1 to n, Cixi, j from 1 to n, Cjxj. We are curious about what is this and what is this. So they are the same things. Everybody here is like the C1x1 adding the C2x2 adding the Cnxn. So everything here is at this term. So eventually, it's a thing that A and B are the same. Once we take the inner product, it's a square norm of this term. And this is a positive, non-negative. So we finish the second requirement. The trick here is that, the trick things here is that actually we are trying to breaking this summation as a square of something. This is a square of something. Okay, so this is our first example. So we will take the 10 minutes break. If you have any question, just you need to ask. Okay, and later on we will we will handle more complicated version. third hour. So in this course, so generally, so I will try to make some change. Sometimes we will do some exercise or give some other tutorial notes. Okay, so we will not just talk about some new content, just follow, do some exercise about this type today, just as a tutorial session. Okay, so our first of things is finish the inner product of as a kernel method. Oh, but you can think about, so what is a phi in this type of function? So in this type of things, our phi is the same as our x, because this is have no difference compared with our least square, our linear function. So this at this moment, phi x is just the x. Okay, phi x is the x. Well, let's just look at more and then think about what is the phi we are actually use. Okay, second one is a kxy equal to the exponential of x times y. And we want to show this one is also a positive kernel. Well, at this moment, kxy is the exponential of xy. Okay. And you can first think about for 1 minute about, so what are two things you need to check? What are two things you need to check? And then we will together to check these two type of things. Think about which type of things you need to check, okay? You must have the same solution as me, okay? So you need to check the symmetric, and then you need to check the sum for any sequence of the xi and ci. We need to guarantee the summation, the quadratic form is non-negative, okay? So this is the two things we need to check. Well, so the first thing is very standard. We need to directly go to the second term. Well, this type of things you will find is pretty difficult, just because this type of the thing is the exponential x times y. And our key idea is that we should breaking the two summation here as a square of something. Well, the exponential is pretty hard to break out, this exponential. Okay. The difficulty is how to handle this. So therefore, later on we will say, why is the reason why we do not pursue what is the phi here. Okay, why we not pursue the phi? Okay, let's just show this together. So commonly, usually, so this actually when we do this type of kernel, we just make some kind of trick. The exponential of xy is hard to handle, but we can put as a, we can try to breaking this type of things as a tight expansion. So e with the power of the, maybe I use a z. Okay, Z. So what kind of thing of this? So it's summation k from 0 to infinity. And it is z with the power of k over k factorial. This is the exponential of the z. And we will try to use this term. Okay. So that is to say, exponential of xy is the sum k from 0 to infinity, k factorial over x power of k, y with the power of k, y with the power of k. And then our summation could be regarded as a summation k from 0 to infinity 1 over k factorial x with power of k, y with power of k. Okay, so this is a little hard to handle this one at the first glance, but we can actually first reorganize the summation. So this is a very, very mathematical trick. The summation can change arbitrarily. So you can put the summation to here. Summation k from 0 to infinity. Summation I from 1 to n. J from 1 to n. Ci, Cj, 1 over k factorial x, y. There's power of k. Wow, I just missing one thing. I should rewrite this one. Just a mistake here. So here, because we focus on the xi, xj, so I should use a xi here. I just change a little bit. So this is a xy, xj, k, xik, xjk. So we do not focus on the exponential of xy. We focus on the exponential of xi and xj. So we change the xi, xj. So accordingly. And then we are wondering how the whole term could be treated as a square of something, how the whole term could be treated as a square of something. Well, so this is also just adopted the same kind of the consideration about. So what if we adding the summation of the single term here? So could this part of thing could be treated as a square of something? So whether it could be treated as a square of something. So this is something we need to answer. So actually, our solution is looks like we can think about what is a square of this term. What is the square of this term? Well, so this is some things we will try to use. So this type of thing is very similar compared with our earlier example. Our earlier example is like we're taking the inner product between xi and xj. So now inner product for one dimension is just like the product. Okay, just like the product. So therefore, at this moment, we just focus on x with the power of k, xj with power of k. So we can treat this as a yi, this as a yj. So the whole term could be this type of things could be treated as a, let me directly write the answer. One over square root of k factorial. Well, it's not necessary to use this guy. I just put at the here. 1 over k factorial. Summation I from 1 to n. Ci xik with power of 2. So this is how the term looks like. How the terms looks like. Well, actually, it's just follows the same standards. We take some time to look at. So how the result is here. So we can ignore the k factorial because it's a common element. We can put it here. So how's the whole element? How we treated the whole element. So there is no trick, just we add the summation one by one. So first we add the sum over the j from 1 to n. At this moment, when we're adding the summation over the j, this is a common vector for any fixed I. It's a common vector. So every element has this common vector. So when we take the summation, so it's just like the I from 1 to n. Summation j from 1 to n, cj xjk, ci xik. Just because when we're taking the summation over the whole part, this one does not rely on the j. It's a common factor. So we obtain this result. And similarly, when we're taking the summation I from 1 to n, this term also does not rely on the I. It's also a common vector. Eventually, we will have the I from 1 to n, ci xik times the summation j from 1 to n, cj xjk. They are the same things, okay, same things. And eventually, that is this term. That is this type of things. So this answer, and eventually, our result, let me split it a little bit. Our result, make a quick summary, is eventually go to at this size. In our example, that summation I from 1 to n, j from 1 to n, ci, cj, exponential xi, xj is equal to k from 0 to infinity. Maybe I also taking that factorial inside. 1 over square root of k factorial. Summation over I from 1 to n, ci, xi with power of k square. Oh, I did take additional bracket here. Okay, and also the same reason, every element here is non-negative. So eventually, we can guarantee this type of thing is non-negative. Okay, so this is also the same thing that when we handle this type of problem, is that we will put as a square of some things, and we can guarantee the whole term is a non-negative. Okay, so this is a little bit more complicated in contrast with our earlier result. It's a little bit more kind of complicated. Okay, so but this is wondering. So this is a very, very typical nonlinear form that we're choosing a kernel as this type is definitely give us a nonlinear result. But how the phi x looks like, how the phi x looks like. So there's some things we actually want to know. So what is the phi x? Okay, so actually phi x looks like this type of things. It's just this type of things. Well, but we just put to the later part. Okay, put it to the later part, and we will show the connection. So the true thing is that the true thing is like that. So later on we will see the phi x actually is something like it's just a very high dimensional vector. So it will eventually also treat it for any element x. It will also treat it to a kind of the matrix. And later on we will see after k, our matrix kernel will be breaking at the 2 phi part. Okay, 2 phi part. And this is also the same thing that when we handle this quadratic form, how we breaking the quadratic form to the square of something. Okay. So this is looks like the C transpose K times C. So if we can breaking the C K as the two sides, C transpose phi transpose times phi times C, and then it will be looks like the C phi square. Okay, C phi square, and this is just like the C phi square. Okay, so this is the idea. So this is the reason why later on I say if you want to know the phi, you must know how to demonstrate a K is a positive kernel. Otherwise, you have no idea about what is the phi you use. Okay, you have no idea about phi you use. Okay, so here, this also just told us one case. So when we handle this type of things, we should try to breaking the phi exponential part, the nonlinear part into other type of technique. Okay. Any question so far? Well, so maybe you can try to do this ones. So trying to handle. So this is an example for you. So you have the 5 minutes to 3 minutes maybe to considering how you demonstrate this one is a positive kernel. Okay, so we can see this one together. Well, we will have more, we will also pick more things as your exercise. So it may not easier to handle the first case. Okay, so here we're using the 1 plus xyz. And the key issue is also same, how we eventually we will try to put as a xi norm with some power and xj with some power. Okay, so let's directly go to the new page. So kxy at this moment is 1 plus xy with power of d. And this term is actually, we can adopt the binomial expression. It's told us how to taking the breaking out this power. So here we must guarantee that d is the integer. D is the integer, okay? D is the integer. So otherwise, it's not easier to handle. Well, so first of thing, we just skip the symmetric. You can directly to handle by yourself. And some things we need to emphasize when we want to handle this type of question, we usually we consider that. So we should note what is the space of our x. So x is a real number. Okay, x and y are real number. So therefore, when we pick the sequence of xi, just follows the same sequence, same space. And also ci. So here I just use the HCI and XI belongs to the real value. And then we will try to show that this type of thing, Ci, Cj, 1 plus Xi, Xj with power of d is non-negative. It's non-negative. So here we will breaking out the pocket. So with a binomial expression that is to see. One plus xy with power of d. So it's a sum L. I just use the d, use the k, okay, use the k. K from 0 to d. It's a combination number. So d factorial over the k factorial and d minus k factorial. X with power, it's not x. 1 with the power of k and x plus y. X times y with the power of. I just use the k. Okay, that's just the same, And usually this type of thing we can regard it as a combination number. D and k. So this is how we're breaking the first term. And you probably know that the following things, I from 1 to n, j from 1 to n, ci, cj, k from 0 to d, dk, x plus x times y, power of k. And we will also handle with the summation trick. Put to the beginning. Well, I just also forget. It's xi, xj with power of k. So you probably know this is the same as the things we handled previously. Eventually, square. So this is our solution. This is our solution. dk. So k from 1 to d, and the remaining part is look at same as this one. We have you handled this one before. And eventually, this is every term. So because this one is a positive constant, this is a non-negative. Eventually, the whole term is non-negative. Whole term is non-negative. Okay, so we have demonstrated the kernel. This is a positive kernel. Well, so this also follows the symmetry, but we can also receive. We can just put a additional stamp, moving a little bit. So is that I mentioned that this term could look at as a. So when we write down this before, this is the C transpose K times the C. Well, I say that when we're trying to demonstrate the C transpose K times C, we are trying to breaking the K as a two part. So it's a two matrix time together. So K is n times n, okay? And actually we are trying to breaking at the two sides. So it is a phi transpose times phi. And phi must be something times the n. Okay, so that our phi transpose must be n times something, some dimension. So we can think about what is the phi in this solution? What is the phi in this solution? Okay, so eventually, just because k could be breaking as a phi transpose phi, and then this solution is definitely equal to phi times c, the absolute value. So it's not absolute, it's a norm, the square of norm of phi times the c, phi times c. C is a n times 1 term, n times 1 term. And this is must be something times 1 dimension. So, and if you look at this type of thing, we can know what is the phi. We can know what is the phi. Okay. So you can answer me, what is the some unknown something here? So what is the dimension of the phi? The dimension of the phi is d plus 1, because we're taking the summation from 0 to d. So this is a d plus 1. And what is the phi here? How the x was be mapping as a phi x. And this phi is just n times d plus 1. And just because this whole term is treated as a phi c, the norm of phi times the c. And it's a case element. So who's a case element must equal to square root of the combination number I from 1 to n, ci, xik. Okay, so this is a case element. This is a case element. And then you're taking the square and adding the k from 0 to d. So that is this same as this type. So this is the case element of the phi times the c. Well, let's just look at more. What is the phi here? So phi times c will result into the summation I from 1 to n with this type of things. C is already given here. So therefore, it's not hard to image that it's resulting to it's the inner product between two vectors. One vector is maybe we use that as a phi k as a vector. So whose value is a square root of the dk x1 with the power of k. Okay, so this is the phi k. So phi k transpose with the c. So the inner product between the phi k and the c will result into this term, the inner product. So like the C1 time here until the Cn time here. So if we put in the or phi k together, that is our capital phi here. Our capital phi is something times the n. So which means that its a column is it has n column. So each column will stand for a value single on the xi part. So therefore, we focus on the different value of the k, like the d0 xi with power of 0 until d x1 with power of d. And we take in the other value d0 x1 with power xn with power of 0 to the d and d xn with power of d. Okay, so this is our capital phi. So give this example, you probably know what kind of the nonlinear function you're choosing at this moment. So every x given to you, it will be mapping to this type of function. Square root of some constant here, x1 with power of 0 to x1 with power of d. So this is how phi x will be mapping. So actually, when we handle our problem, when we adopted this kernel and using every method using the previous method we mentioned, like we solving the C star, so with k times n times lambda times identity inverse and times y. That is our C star, and then we use a C star backing to make the prediction. It's the same as we're using this kind of phi. We first do the transformation on the phi and adopted the ridge regression. So that is the same. So this is how this kind of the kernel using here, how the kind of kernel is using here. This kernel explicitly told us. So actually, we didn't just told you where is the basis function, how you make the transformation to x to phi x, but we explicitly to adopt it every d dimension, every d with a power, every d powers polynomial term. Okay, so let me back a little bit. What is the phi here? What is the phi here? So this type of thing is probably explain why we do not adopt it. We never say what is a phi, the explicit form. You can find when I say the dimension of the phi, I use this unknown to stand for, and this unknown it turns out to be how many summation is taking here, how many summation is taking here. So therefore, the previous phi is a infinite dimension. So it's an infinite dimension. It's actually phi is a very, very long term and it's infinite. So, and you're trying to adopt it, any element xi with a power from 1 to infinity. So that is how the exponential kernel using, okay? So it's infinite, but infinite is sometimes hard to describe. And actually infinite kind of basis is not useful just because we only have the finite sample. So therefore, sometimes we just play this type of trick, okay? So later on you will see what is the trick it is at the end of this chapter. So the kernel trick just a very beautiful result that we do not handle this infinite dimension phi. we just change a little bit with some kind of the linear algebra, so to avoid handle, and then the result only focus on kernel. So this is the thing I put at beginning. So why we only introduce a kernel and ignore the phi at this time. Okay, well, so if you look at some other kind of machine learning book, you probably will know you will starting with a phi, and then you will find usually it's hard to describe what phi is. Well, maybe we just take one additional example. Okay, take one additional example. Okay, you can think about how you handle this type of thing. So x times y times the exponential of xy. So it's pretty similar like our second example. Okay, so let's look at together. Well, this type of things almost use the same trick, almost the same trick. Okay, we also just write down stem by stem. Kxy is the xy times the exponential of xy. First, we demonstrate the symmetric, so that is straightforward. And the second thing is that we will show any sequence of xi, I from 1 to n, with a ci, I from 1 to n. Then the summation I from 1 to n, j from 1 to n. The resulting that ci, cj, xi, xj, exponential xi, xj shall be non-negative. Of course, here we adopted the same things, That is, we considering the title expansion again. This term is what then be writing down as a k from 0 to infinity with a k factorial xi with power of k, xj with power of k. So therefore, we can first combine this term with this term. So to make it as a k plus 1 dimension, And then we can make a quick organize k factorial. Well. So that is a term like ci, cj, xi with power of k plus 1, xj with power of k plus 1. And the same trick, okay? Same trick is ci, cj, xi with the same xj with the same power. Then we will making it as a square of something. Okay, and then we obtain our result. So it's a non-negative. Okay, non-negative. Well, and one thing we can do again, so is that where is the phi come from this type of function? So where is the phi? So here I just mentioned this phi must equal to phi transpose times the phi equal to our k. And this whole term is corresponding to c transpose k times the c. So you may be curious about why I put here, but eventually, I just emphasize, eventually we will show that k must equal to these two. And also this k could be breaking out as a two matrices times together is the equivalent as it's a positive kernel. So this is the equivalent as a positive kernel. You can see once you could write it as this form, it's first implies a symmetric. Second, it's imply the eigenvalue is non-negative. So this is the same as in our previous chapter when we handle the A transpose times A. It's not, it's Z transpose times Z. So we have show, when we do the singular value decomposition, whose eigenvalue of this Z transpose times Z? Well, Z transpose times Z. The eigenvalue of this term is the singular value, the square of the singular value of the Z. So therefore, it's a square of some things, the eigenvalue of the K. So that is a semi-positive kernel. So that is a semi-positive matrix or the positive kernel. So this is the reason. So these two things, why we have this requirement, just trying to, it's equivalent to it could be breaking. But wondering what kind of phi here? Well, you can think about, we also keep the same, that this whole term is a phi c. No, just because it could be, once it could be breaking, this term could be regarded as a normal phi c. Square normal phi c. So what is a phi c we're using here? So let me just show, okay? This is the reason why I say I didn't want to mention the dimension of phi. Dimension of phi must equal to something times n. In this example, this something is infinity. So infinity times n. It's very hard to describe, but what is that? But just a huge things. And then what is the single x was be mapping? The single x is be mapping as a infinite dimension. So whose element? The first element is a k equal to 0. So that is a 1. Oh, it's not a 1. It's a x itself. This is the first element. When we're taking the k equal to 0, okay, so this is a 1. 0 factorial is 1, okay, so this is a x itself. And then we're taking the 2, taking the k equal to 1. And then it's a x squared. And then is a so on and so forth, is a k factorial, square root of k factorial, x with the power of k plus 1. And then we try any integer of the k. So therefore, the phi x is a pretty long thing. Pretty long things. It's an infinite dimension. And then once you adopted this type of things, so you can, so this is the y, this is the first element. So we consider the x. Then we have the our phi is the infinite norm times the n. Just stand for we mapping it to the phi x1. We just putting this term. Our capital phi is a phi x1 to phi xn. This is our capital phi. Okay, so phi x1, phi xi, so inner product with the ci will give. So each row here will inner product with the ci give us this type of element. Okay, so this is the reason the phi is an infinite dimension and it's trie. A lot of square, lot of the polynomial term, and with some little bit difference is a factorial here. The 1 over square root of k factorial. So earlier one is well, this type of things, or is this type of things. So a little different coefficient, is a different coefficient. Okay, we still have several examples, and we will put this example in the next week. Well, so maybe we just stop here, and if you have any questions you need to ask, this one is more complicated compared with the previous chapter.